Salutations to 16ers, this is Professor Kaufman, and what follows is an introduction to Project 3. This project will be the one and only project that features assembly coding and working at this low level, but it is a bit of a doozy, and past students have found it to be somewhat challenging as they transition from the high-level languages, particularly C that we've worked in up to this point, and then getting into the nitty-gritty details that are associated with assembly. To make this somewhat easier, the project is structured more or less exactly as Project 2 was structured. There will be a problem which reworks the battery meter functions that you wrote in C at that point, except writes them in hand-coded x86-64 assembly rather than C, as was the case in Project 2. And then a second problem that involves a similar setup to the puzzle box problem that had been solved previously, where there's a binary executable. The source code for that is missing, so all you have is the executable to work with, and we'll need to make use of GDB to analyze it, but it has a certain set of correct inputs that would allow you to solve it and earn credit as you go through various phases there within. And that is lovingly called puzzle bin instead, as it is binary only. There is no tree problem in this case, rather these are what you'll be up against solely for Project 3. So the domain of both of those is already familiar, and that should ease the path somewhat, but coding these things in assembly and then analyzing and working to debug an assembly program will give you an appreciation for the high-level nature that most other program environments provide, while also exposing you to this is what actually happens under the hood, which is essential knowledge for any self-respecting CSer out there. So, as usual, there is a code sort of pack along with various files in it. Many of these will already be familiar to you as they're replicas of what was distributed as part of Project 2 and the battery problem. And as well, there'll be a puzzle bin program to run and an input.txt that has some dumb stuff in it that we will immediately start replacing with personalized stuff. So the overview video is going to be structured as going through each of those two problems and sort of getting started on them to get you oriented there. They can be taken in either order, and a lot of students will work on one for a while, and when they get sort of tired of it, take a break and then work on the other one. So choose your own adventure in that respect. You're only responsible for creating a single source file, particularly if you finished Project 2 and are happy with your bat update.c version there. You can just copy that over and use it as a reference. The only file that you need to create in this case is bat update asm.s. There is a provided input.txt, and that's the only one that you'll edit in order to work through problem 2. All right, let us get into it. So in problem 1, you'll be rewriting set bat from port, set display from bat, and bat update, these three functions that you wrote as part of the original battery meter problem, rewriting those in x86 assembly. Now, this is a big change, and it will sort of behoove you to have straightened your C code out and be as, as concise, I'd say, concise as possible with that C code. That's the source of the line limits that were in place in Project 2 on that C code. But largely the functionality is identical, and the test cases are more or less identical to what's been there. So if you need to get reacquainted, then refer back to the Project 2 specification with the pictures of where various bits are at and so forth. Nothing much of anything has changed in terms of the assembly code. Now, a few provisos as we get into this, because there is the potential to sort of engage in some shenanigans here, and we want to head that off. Hand code your assembly. So no credit will be given on manual inspection if it appears that you have used some compiler-generated code and tried to submit it as your solution to this. As most of you should be aware at this point, part of what GCC does is to translate C code down to assembly. And I'm not discouraging you from looking at the code that GCC would provide as it would compile your C code down to assembly. However, that is machine generated and is not particularly easy to maintain. So rather, we'd be looking for signs of hand-codedness in that. It's a good idea to base your overall approach on your C code there, but we'll be looking for certain signs that the hand-coded sort of features, if you will, that you actually went through this exercise of translating it on your own to get an understanding of what the compiler will be up against. So these will be things that are sort of listed out over here, such as annotations that are fairly thorough. That is commentary, use of labels that make sense, subdividing things into sort of smaller blocks instead of having one giant straight line bit of code. Those blocks have maybe a top comment that says the intent of the next thing is as follows, and potentially then comments associated with lots of lines to describe what the flow is like. Well-named labels to indicate what the purpose of sort of why would I jump to this spot in the code, and use of the division instruction. Generally speaking, GCC would not do any of these things. Would avoid division if it could figure out a way, and it has lots of tricks to do so. Would name its labels like L1, L2, L3, would not provide much of any comments, and would not subdivide things very well. Would have all kinds of sort of jump around as it would optimize the output assembly code. Now, in the event that you struggled to get a clean solution on Project 2 to this bat update.c, for this project only, you may visit an office hours and talk with a staff member about what you struggled with on this, and they will then show you the bat update.c file that is part of the solution that the instructors have, and then provide that to you as a reference that may be a more sane guide of how to translate things to assembly. That's if you were dissatisfied with your Project 2 solution, and it's a good idea if you were to do that earlier rather than later. We sometimes have students come in the day that Project 3 is due and ask for this, and it doesn't do you a lot of good at that point because you'll be well behind schedule there. A few general cautions on assembly, and I won't belabor this because a lot of what we do in lecture is about this, but it will take some effort. And so various mistakes that are frequent among students are listed over here. For instance, inadvertently forgetting to put $1 in front of constants, which means a raw memory address, likely a seg fault in most cases. Use those dollars there. Set up your editor so that you can comment things. The most common things in C syntax highlighting, there's a little YouTube video here on how to do that for VS Code. The most common comment from students about past students to present students about what they should do is comment the crap out of your assembly code. Like, you will easily, between sitting sessions, forget what your intent was, forget what variable was in this register and so forth. So being very diligent with commenting on that stuff is a good thing to do. Make sure to be cognizant of where arguments come into functions, and that there's this division in the registers between caller save and callee save, and you'd want to favor the caller save registers as you're using them in code, and if you run out, then you have to take some special steps to use the callee save registers effectively. We'll be discussing those things in lecture and lab, so to get you aware of it. And then there are a few other things on here that are sort of worth mentioning, how to do division, how to extend the stack when you need local variables and so forth, and then our friend the register diagram to apprise you to some of the special features of each of the registers that are there. Make sure to allot some time and do so over the course of several days as you work on writing that code, as it will be a bit of a bear. Now, to get started, we'll need to create an assembly file. So in a moment, I'm going to download the code pack and then copy this provided template in as a way to start for that. That contains stuff that can't compile out of the gate, but we'll make adjustments to it and provides then the assembly equivalent of prototypes for each of the functions that are there. And we'll, as well as that, a little data section where we can put some global variables like most of you in Project 2 will have used some sort of an array of bit masks or bit patterns to constitute how digits are supposed to be displayed. Copying this in allows you to sort of construct that with relative ease. So the remainder of our project spec has information about, to remind you about things, and in particular you may wish to refer back here to stuff that will be in the provided header. It was absent from Project 2's stuff, but is necessary now, that relates to the layout of the structs that's at the center of problem 1, this bat-t struct. It's relatively small, only 4 bytes big. But at the assembly level, you'll need to operate on its fields using some assembly level syntax that we've talked about in lecture, have demonstrated in lab, and now you'll deploy on the project. That differs based on whether you have a pointer to a struct or a packed struct there. In the first case, you'll want to dereference and grab fields or set them. If you were, for instance, trying to set things associated with that, that would be assembly syntax that looks like this. And here, this reg has a pointer to wherever that thing's at. You'll have to know which register has that pointer, of course. But these instructions would then place things out there according to the byte offsets that are given for it. But in contrast to that, if you have a packed struct, then you'll need to do some bit shifting and masking in order to extract the fields there. If you're paying attention, you'll have noticed that, oh, the first function has a pointer to one of those structs, and the second has an actual struct that's packed into a single argument register. And so to that end, both those sets of techniques will be useful, and we might turn our attention there to that. There are a bunch of automated tests, some manual inspection criteria for that, and I think it's worth mentioning that if you get everything right, all tests, and get full credit on all the manual inspection criteria, just by virtue of that, you'll earn yourself 5 makeup credit points, as it's a somewhat difficult assignment there. Okay, so let's get into it and actually do a little bit of coding on this. I'm going to copy the link to this code pack here, copy a link address, and I'll zip over here. Pull up a terminal and do a wget here. That should leave here the p3 code.zip in the directory, and I'll unzip that thing. And if I come over here, I should have this p3 code now, and you can see absent in here is the bat update underscore asm.s. Now I'm not going to bother to bring in my bat update.c from my other projects yet, because that's mine and I don't necessarily want to see you to see it. But I should create that file called bat asm.s. So let me just copy this bit right here and use whatever mechanism your editor has to create new files. In this case, it's just for me, find a file that looks like this. And then we're gonna, let's see, zip down to this structure of the bat update asm file and start copying some stuff here. Okay, copying here. Now my text editor is configured to be able to show x86 assembly properly, so I'm seeing one color for labels, another color for assembler directives, another color for the commentary that's here. And so if you don't see things like that, now would be a great time to configure your editor so that it has that feature. It's just installing a little extension on VS Code, which should take you about 30 seconds. As for us, this won't compile out of the gate because there are several things that are uncompilable. For instance, this instruction is for guidance rather than being actually workable. The move X, of course, is no good. Reg is not a valid register, and so forth. So I might wish to just comment that out right now to sort of see that and make use of it later. Most of you should remember that setBat from ports was going to analyze some global variables and then fill in a struct associated with it so that the values in it reflect the state of the sort of global machine there. And to that end, we'll need some syntax in order to access those global variables. This is one way to do so, but we'll have to sort of tailor it a little bit. And I don't not of a mind of that right now. Right now, I just want to run the test cases to see if it's okay. And if I zipped over here, change my p3 code. Let's see, I'll save this thing, and then did a make test prob1. I'm probably not even going to get anything. It's like assembler messages. Yeah, there's no such thing as this instruction. So to that end, I'll also want to make a few changes here. There's a mention here, don't forget to return from functions. Assembly is a little bit weird in that straight line code here, but you jump to this function, it'll just execute through, and if there's nothing here, it'll fall through to try to execute code that's down here in a data section, and that's just no good. So I'm going to plop down a ret right here. Maybe I'll even do a move $0 into EAX. I know for sure that's the return register where return values are stored. And so this will set up that return value properly. In each of the functions here, set bat from ports, set display from bat, and set bat update, they return integers. You can see that in the header over here that they're mentioned up here, but each of them returns an integer, and so I may as well just do what I just did a moment ago for each of those functions to pop down a return along with a return of 0 here. Okay, this data section we'll revisit in just a second. Here's where the code would start for the set display from bat, and I'll plop down my return right there. And then here, this is where bat update would start, and I'll plop down another return here. Now, if you're noticing anything over here, I see. Actually, I think I noticed something that I will need to change in this template, which is that we're in text here, and text in this case is the executable text of the program, and then a change to data over here, and I forgot to change back to text here. Let's see, so here, if I don't do this, I could get problems. And so that's an excellent thing to plop down here. A directive to say, hey, assembler, what this stuff was data, sets up global variables in assembly. This part says we're switching back to code now, so put this in the executable portion of the assembler. Without that, things could go haywire, and so I'll definitely want that over here. Now, it's possible that there are a few things yet remaining in here that are not right, but let's at least ask and say here, like, oh, no, okay, so that worked out okay. Now, all failures, as is usually the case here, but hey, at least the tests are running at this stage. One thing you'll note is that there are 40 tests, but they're only worth a half point apiece. And so the total here is 20 points for the automated testing. And then there's quite a bit associated with the manual inspection there. The tests are, reasonably comprehensive, but this is, yeah. So just be aware of that part, that it'll be possible to get like 11.5 points on the testing here because they're only half points a pop. Okay, so then the next step would be to take a look at this set bat from ports and try to recall what is it supposed to do. You might pull up your C code in order to do that. I'm not going to do that now because that would reveal my solution to it. But I can reason through what more or less it's supposed to do again. And for that, I'm going to turn back over here to the documentation that's associated with it. So it's supposed to use these two global variables, bat voltage port and bat status port, and set fields of this parameter bat. This bat is a struct. It's passed in via a pointer to the memory area where it's located. And so it's to the function in its entirety is look at these global variables and then set some fields in here. Again, the fields that are in there are a number of millivolts, a percent, and a mode. If you don't recall the global variables, they have certain characteristics. For instance, this bat voltage port, it measures the voltage on the machine that's coming off of the battery in half millivolts. So we need to divide by 2 in order to get the right voltage level that's associated with that. And then the bat status port has a particular bit in it that indicates whether or not the battery is to display this stuff in volts or in percent. And I'm not sure if it says in this documentation. Yeah, it says elsewhere in the documentation associated with that global variable which bit it is. I think it's 4 if I remember right, but we'll look back at that in a second. Let's just futz around a little bit here, and we can come back up here to the code here and uncomment this little bit of syntax that was given here that has to do with how to access global variables in assembly. We'll talk about this in more detail in lecture, but this is a sort of odd incantation in order to access a global variable. A few things that you might immediately sort of recognize is some global var here. That's one that you don't want to use that word because it's not a valid global variable. Instead, I get rid of that and plop down here like this bat voltage port. That's the one that I'm interested in this case. Now, the move X here also needs to be replaced, and that's got to be in concordance with what's the size of this local variable. And to that end, if I come back over here, you can check again, it's a short, it's a 16-bit quantity. And so here I'd want to use a move W. Using a bigger move than move W, like a move L or a move Q, would grab certainly this variable, but also any other nearby data, up to 4 or 8 bytes associated with that memory area. And there are only 2 that are associated with this variable. So that would maybe inadvertently bring in things like this bat status port or this bat display port, depending on the way the compiler orders those global variables in the data area associated with the executable. Then we bad mojo, and so we'll need to make use of a move W. And then finally, I would also want to plop down an actual register here. Now's not a bad time just to recall, set bat from ports, it takes a single argument, this bat t over here, and trying to remember, okay, where does that single argument come into this assembly function? You should hopefully vaguely recall at this stage that for small numbers of arguments to functions, up to 6, they come in via registers only. You'd be forgiven at this stage if you don't remember exactly what they are, but hey, there's a handy diagram for that, and RDI is going to be our go-to here. It's the first register used for arguments. And so I might make a little comment up here. Say RDI is the pointer to bat. Something like that. Well, I don't know, is a bat pointer to bat, something like that. Anyway, good enough here. So whatever register I pick here to say, hey, I need to move this global variable into that, that's not going to be, I not want to overwrite RDI because that's the only one that's got anything in it, and losing that would be bad mojo. So for the moment, I'm just going to pick a different one. Let me pick RSI here, something like that. Okay, zipping back over here, let me do a make test problem, and I'm just going to work on the first problem here. Test num equal to 1. And the first thing straight out of the gate is the assembler is not happy with my use of registers here. So at line 10, there's an incorrect register SI used with the W suffix. That admittedly is an intentional mistake. Just to get you to recall, when you use a movement, in that instruction or lots of other instructions, the assembler will check that this suffix is in concordance with the register size given over here. RSI is a 64-bit register name, but the movement size is only 16 bits, 2 bytes. And so in case you forget, you can zip back over to the register diagram and say, well, I need here for RSI, what is this 16-bit name? It's listed here, and SI is the 16-bit name. So let me plop that down here. Cool. Now that's not a lot sort of to go on so far, but I would probably want at this stage, just to make sure everything's going right, I'm going to run the test case. I don't expect to pass it or anything like that. But hey, it's running and I can see some output and there's a bunch of stuff over here. The one thing I wanted to call your attention to is if you want to see what's happening at this stage, then it'd be a good idea to fire this up in GDB. And there's a command line given here to say if you wanted to run this exact test case in the situation that is sort of pertinent to the test case, here is your invocation. You can add other things like a -2e to it and then set breakpoints and so forth. I actually kind of want to do that. So I'm going to copy here that stuff and just look, okay, the voltage port is set to 0. So as I move that into this register here, SI, I want to see a 0 there. And so I can just at least verify that part. And it might make more sense to do this a little bit later, but oftentimes students write a ton of assembly code and then have no idea how to check like where things are going wrong. A good way to do that is, hey, copy that line, paste it in here. I'm going to add the 2e part to this, and we'll be doing a lot of that for problem 2. And I've got source code both for my assembly and for the C code like testing stuff in this case, so I don't need anything special. I do want to see what my function is doing, and in this case, the test is evaluating set bat from ports. So let me break there. It's set bat from ports, and you notice here if I type a little bit of this and then press tab, GDB is aware of the different symbols, functions, and global variables, and so I can tab complete that kind of stuff. And at this stage, I can just run. And the screen gets a little bit gobbledygooked, but pressing Control-L will modify that. I don't need to do anything by way of like the source level stuff because my assembly is in source, or the source is assembly in this case. But I would like to see the registers, so let me shift over to layout regs here. This isn't all of the 16 registers, so let me just decrease my font size a little bit more. It's probably not great for those of you who are watching on a small screen, but at least I can see most of the registers now, even if it's a little bit invisible. So on executing this instruction, you would expect to see a change in the RSI register that's up here. And if I step an instruction now, step I, or as a shortcut, just SI, you'll see that parts of this did change. Now the test, as it was looking at, it says the voltage port is 0. And you'll see this 16-bit number, there is a 0 there. But I also see a bunch of garbage up here, which is not great. This bad thing, that's more or less how all of the registers are initialized as it comes into your function, except in this case RDI, that's a pointer to one of these BAT-T structs that we're to initialize. So we're unfortunately getting pinched by one of the features of these small move instructions, move W. That's grabbing 2 bytes from global memory and copying it into SI, but small moves like move Ws and move Bs, they don't overwrite the whole register. So unless I'm super careful, I will possibly use all these bad values up here, which are hex, and that's going to screw up any mathematical calculations that I might do later on involving this register. So let me retrench. I'm going to come back over here and just say move a 0 into RSI to begin with. And that should initialize it to be 0. I'm going to need to step out of the debugger. And here's a nice trick to know if you're doing such things and you've got just a single terminal available here. If you are in a program that takes over the screen, like GDB does here, if you press Control-Z, this will suspend that program and give you your terminal back. And that will allow you to do things like, oh, I could type make again. And this would re-update all of the programs based on the changed assembly I had here. Or rerun one of the tests that are over here. Make test prob 1, test num. This is still going to do other things here. Now, that's to say that there are still some programs running. GDB hasn't gone anywhere. Control-Z didn't actually quit it, it suspended it. You can ask around like, hey, what jobs are running right now? GDB is still in the background over there, like waiting to resume control. And the keystroke or command to do that is to move it to the foreground here, FG. You'll notice the one over here, you can suspend several of these and interchange between them with like %1 for the first job, %2 for the second job. But if you've only got one, in this case GDB, you can foreground it. And this will bring us right back into the debugging session. So I can rerun this time. Hopefully this will detect the change in the executable. And I'll know that for sure if I see now this new instruction, which wasn't there before. This thing is going to, let's see, should overwrite all of RSI here with a 0. So if I step an instruction, yep, it does. And now this time, if I step a single instruction, I see 0 still there, but it plops down to 16 bits of 0. So if there was a non-zero quantity there, as would be the case in a different test case, then this would show up, but I'd have exactly that number in RSA at this point. Cool. The only other thing that I might want to do at this stage is to say, hey, let me take that value, RSI, that I just got from this global variable and copy it into the location associated with the millivolts for this thing. So in that case, I've got it in SI, and I want to move now SI, this 16-bit quantity, to where that BAT-T is located. Oh no, this isn't going to be completely right because I haven't divided by 2 yet, but it should be reasonable at this stage. So I need to know where that's at. And over here, if you consider the documentation, there's a field access table over here for if you have a pointer to the BAT-T and you want to access its millivolts. That's 0 bytes off of where the pointer points to, and you want to move 2 bytes there using a move W. So let me just grab this thing over here. And all I'd have to do then is to change, oops, let's see, I've already got the, I don't want 5, I want SI out there. I could try 5, I might try 5 in just a second, but I need to change this register to where do I have a pointer to this thing, and thankfully I just documented that. It's like, oh, it's up here in RDI. So I'll plop down DI here. And since I know this is 0 here and I want to see a change, let me just comment this thing. And instead move like here's 57 to that spot. So I can actually see it change. That should show up in the test case there. Okay, so then I'll come back over to the terminal, temporarily suspend GDB because I may want to come to that, and then rerun this test again. I can probably increase the font once more. Let's see, and I'm going to scroll. Oh, crap. Okay, let me just reset my terminal here because sometimes programs like GDB that take over like that, they screw up the scrolling and so forth. Scroll way back up here. And indeed, see, hey, you put a 57 out there. That's great. That's what it's supposed to be. Or, I mean, it's not supposed to be that, but it can actually affect the struct that's given back. Got the right return value. And so we're somewhat well on our way here. If I'd moved 0 here, I'd have that right, but would also need to change the percent in the mode correctly. And again, you can't just move that to that spot because the sensor port is going to be twice what the voltage is. So you need to divide by 2 there. And there are smart and dumb ways of dividing by 2 when you're at the assembly level. The dumb way would be to try to do the division instruction, but recognizing the power of 2 as shift is probably more appropriate there. Okay, one last thing to do associated with this the problem 1 is just to talk through on the horizon what the second function looks like. Now I want to spend a little attention on that because it does something the first one doesn't. It needs to use some kind of data. It's possible to lay out an array of some sort in the stack space associated with this set display from BAT, but it's not really necessary. And it's somewhat more palatable to say like, oh, here's syntax up here that gives one a way to lay out global arrays. And then if you're acquainted with syntax to get a pointer to that global variable into a register within the function, then you can access data that's stored in globals up here and make use of it as your sort of code progresses. So it should be obvious here then, like, oh, this myArray thing, it shows here's an int that's 20 or in hex or in binary if you want. And so if you laid out similarly, like here's a, let's see, a number bit mask array, something like that, maybe a bit verbose, but no matter. You can lay out things like, how here's an int 0b110110. Let's see if that is 1, 2, 3, 4, 5, 6, 7. I think all of those were 7-bit quantities, so I'll plop something like that. And then here's maybe that's the pattern for 0. So I'll put it like this, 0. And then here's the pattern for 1. It's like, you know, there's a 1, 1 here, something like that. I don't remember if these are the right patterns or not, but you can sort of fill in based on your C code. And then a 2 here, maybe that's like a 1 here and a 1 here and a 1 here, something along those lines. So make use of the bit patterns that you laid out over there. Then this becomes something that you can use in the set display from BAT function. The syntax to access that is going to be described in lecture, but just as a sort of brief review, and I should probably add this to the project spec, if you wanted to access this array, it'd be a good idea to load a register with the starting address for it. And so it's a global variable. Let me copy up here the name for it. We learned earlier that has to be done via an offset from the RIP. And in this case, I want to load up some register. I'll randomly pick RAX with that. And so this is the beginnings of it. Now, a move in this case would have to be a move L that would move some element of this array into, so the beginning element in this case, this 0, into RAX as an integer. But I don't actually want to move this element here. I want to say, what's the address of this 0th element? And for that, the load effective address instruction is super handy. We talked about this in lecture as associated with address computation, and it would do something along the lines of sets RAX equal to the address of number bit mask array 0, like that, or if you're using sort of bare names, then just be number bit mask array, but it's the address of the 0th element there. And that's handy because at that stage, you can use that three-part syntax to say like, oh, RAX is the beginning of a pointer. I have some other register that has an index into it, and I know the size of the register is 4. This syntax will allow access or changing of these, and generally you'd want to access them. So recall those things from what we've done in lecture, as they'll be useful. Not immediately in this, but at the stage that you're trying to start constructing your display by extracting bit patterns from here and plopping them down, shifting them around at various spots into some sort of central variable or register that is going to be the ultimate display and bit patterns that you select. Cool. That's all I want to say about problem 1. Allot yourself quite a bit of time to work through these things and rely heavily on the labs that you've done up to this stage, as most of them will provide various kinds of techniques that will be combined here in full in order to accomplish a somewhat larger task. Let us turn our attention now to the second problem, and this is a debugging effort. So there is in your code pack a program called PuzzleBin, and if I zip over here, you can see what it looks like. It's here, PuzzleBin. If you open it up, it will look like an executable, which is to say any sensible text editor is going to show a heck of a lot of gibberish here on it. And on the command line, if we were over here, if you were to run it, it would simply state I have the same basic calling interface as what PuzzleBox had, that you're supposed to provide an in file here. The template version of that is in input.txt, and you can see you're supposed to put in your directory ID. I'll comply with that and plop down COF095, my old student ID, when I was a younger and less gray man. And the remainder of this file then is to be filled in. As a hint, the first line is looks something like this as a sort of free-form text. And so I'll leave it as is, but I should save it right now. Running PuzzleBin on that input.txt, now that I've actually entered my directory ID, you can see I didn't get anything out of this. Some encouragement perhaps, but no points so far. And at that stage, it could be very sticky if you didn't know what we're about to sort of discuss in terms of GDB, that it can analyze binaries where there is no source code for this. So don't look around for like, where's the source code for this thing? In fact, you should sort of fully expect the following, that on running GDB in TUI mode on PuzzleBin, you'll see this, no source available. That is completely and totally expected, so don't ask about it. Folks just snicker and say, deal with it. Instead, recognize that this source code is not necessary if you know something about assembly, and know that in the midst of the debugger, you can ask, hey, show me the assembly mode for this, and it will disassemble that executable and show you here are the instructions that are in here. Now, it's starting at main, and that's sort of natural, like this is where all execution starts, but generally speaking, you don't need to spend a lot of time on main. Instead, you need to spend time on the phases that are in here. And as a shortcut preview, that you should know that like, oh, you set breakpoints, you can actually break out a lot of spots. There are 200 possibilities in here. But if I start FA, or PH rather, there are 7 phases baked into this and are places then that you'll probably spend time. They go in order, so phase 1, phase 2, phase 3, phase 4, etc. And each of them has a number of points associated with them. If you're curious, you can scroll down a little bit and see the table of these are the number of points associated with each phase. You only need to complete 6 to get full credit, 40 points. But if you complete more than that, including one that isn't listed here, then that's worth some additional makeup credit. And if you get stuck at any point, you can skip phases at a minor penalty. Just be cognizant that skipping changes the state of the random number generator that's in it. And so it's a sort of permanent skip where the answers you get later on, they'll earn you points. But if you go back and, oh, I figured out how to do phase 3 now, the answers you have for 4, 5, and so forth, they may actually be different now. But hopefully you'll have locked in the techniques to how to do that so you can quickly derive new answers for it. So that should encourage you in some ways to spend time actually understanding what's happening there. To skip phases, put as your input just skip there. So for instance, if I were feeling super lazy here, I could just put down skip for this first one. And if I zip out of the debugger and run it on this, then you'll see the skip message here, and I've got -1 out of 40, which is not great there. So basically go in order unless you really need to sort of wait and get help on something. Just know that you'll probably have to get a slightly different answer for later phases then. Okay, let me undo that thing here, and then let's start talking about how you would actually go about analyzing this. So let me set a breakpoint at phase 1. And then I can run. I'll need to run with the input.txt or set my args to be input.txt and then run. Either one of those would work out fine in this case. This will run ahead, screw up the screen because there's a little bit of output printed over here. But if I refresh, you'll see we've hit a breakpoint here at phase 1. And there's going to be sort of a proceeding of assembly instructions that will check to see if the input that's coming at input.txt matches expectations. Now, our first and foremost goal in this case is to figure out what are those expectations. Like, how do I figure that stuff out? So I'll give some advice on that and some hints here on it. You can see that phase 1 is not particularly long. These sort of instructions here are all associated with phase 1, but then phase 2 starts immediately after that in terms of code. What we'll want to avoid is this failure path that's over here. Now, I could just start nexting some instructions here. If you do a step instruction here, you're going to step into this next line routine. And while you may be interested in sort of looking at that part, literally like this function is meant just to get the next line, and it's somewhat complex in that respect. And so all the callable functions are here, they're by and large, like they do what they say they're going to do. Now, understanding like what they do sort of at high level will be important to making progress on this. But I would not recommend stepping through all this and trying to understand what's happening there. At the outset, you should understand this was a C program that was compiled down to assembly. So we're looking at GCC generated instructions. They're not meant to be particularly easy to understand then. So in that respect, I'm actually just going to restart run this thing because I don't want to go through that. Instead, I want to pass over it using a next instruction. Instead of stepping in, I'll next over it, and then consider what might this have done. Now, it didn't look in the preamble here like any parameters were passed to next line. It's possible, maybe, that there was like something in RDI, and RSI that got passed in over here. But at this stage, those things would have been lost because it's caller save register and there's no save of it anywhere here. And rather, the only information next line could really have conveyed back comes from the return registers. And so that register is RAX, and you can see something's immediately done with it here, which really speaks to the fact that, oh, this might have returned something interesting. Now, at this stage, I might be sort of curious about it, and in that respect, it wouldn't be a bad idea to look at those registers and how they change over time. And so I might plop down the registers, so do a layout regis to show here again are some of those registers. I'm not going to bother to expand the sort of collection of these because these ones that are listed up here are sufficient for now. Let me rerun one more time from the beginning. And if I do some next instructions here, you can see that, yes, across this call boundary, several things changed, including RAX. Now, this looks like a really big number. However, it looks like a reasonable memory address. So with the 7FFFF7 thing, you'll start to get used to like, oh, on a system, memory addresses have a certain sort of characteristic to them. And high memory addresses like this, they're oftentimes stack addresses. We talked earlier about how the function call stack is high up in memory, and this is quite high. RDX looks like a number, but I don't want to rely on anything else over here because the only thing that should really come out of a function call is its return value, and that's an RAX. So it's not a bad idea at this stage to start poking around and saying, okay, this RAX, like what might it be? It's clearly being copied over to RDI because if I stepped a next instruction, you see, oh, that changes RDI here, now matches exactly what RAX was. and then something else is going to happen. So let's examine like what might that RAX be. Here are possibilities. It's a number. And so I might say, okay, it's this number, that doesn't make a lot of sense, or this number, that as a hex value doesn't make a lot of sense. Like numbers, I think of as like, they're numbers like this, they're relatively small. So if this is a memory address, then I might start guessing about like what is at that memory address. Maybe it's a number. And so I do something like examine. This is examine a memory address. Examine it as a decimal number, for instance. And the place that I want to examine is in the RAX register. Note the little $sign here. That's the notation that GDB uses to work with registers as special values. So this is going to go to this memory address and say print out what's there as a number. That as a 32-bit number doesn't really make a lot of sense, so I guess not. If it's not an integer, maybe it's a string. And so I'll try examine that same spot as though it were a string instead. Ooh, now that is interesting. Okay, so we just learned something important. This function, it returns something. It returns a pointer, and what it points at that location is probably a string. And to boot, the disassembler, or the GDB actually knows something about, oh, this is in some region that's called inputs. And so that how now brown cow thing, that's what was in my input.txt. So this next line thing, I read a line out of that, which I guess maybe in retrospect we could have just guessed at here. But that's a powerful technique to say like, oh, this register points somewhere, let me poke around and see what kind of stuff it points at, sometimes strings, maybe numbers, we'll see. One thing I should note is that, hey, the x/d here, it will default to a certain size, usually an integer, but you can change this to be like, oh, print it not as a word, or as a decimal or as a word, but print it as like, let's see, a byte. Let's see, so this would be 72. Now my guess is that's the ASCII code for H. And so this says print it as a byte in decimal format. And we might want to sort of check on that, but I'm pretty sure 65 is A, so that seems about right to be H somewhere in there. And so being mindful of the fact that you control sizes for that, and it's actually stateful. So if I just say D now, it'll stick back to 72. To get back to 32-bit, I have to go back to a word size here there. But we know it's not a number, but we know it's a string, so there it is. Now, moving forwards, this little bit of syntax over here should ring a few bells. We just moments ago saw that, oh, when you do something that's an offset from the RIP like this, there's usually words right here. In this case, there's some sort of a hex number there. And in truth, this is going to be a global variable access because the word that I might have used, like in the assembly code that I had over here, I used this word number bit mask array here. That gets translated to a number which is the offset into the global variables table of where this thing is located. And so this is some offset, and I don't know what the name of it here is based on this, but GDB does, in fact, knows that like, oh, this is the raw address that's calculated from adding the current RIP value onto this hex constant. And there's a symbol that's there, it's called quote. And so there are a couple ways I might access it. I might type this thing in. I might try to do some addition here, although it's a little squirrely with the RIP offset and so forth. But the easiest way is just to acknowledge, oh, this is copying something into RSI. And so if I just step an instruction, then RSI now has a memory address in it. And it would be worthwhile to analyze what that memory address is. Now again, this could be a pointer to integer data, it could be a pointer to a linked list node, it could be a lot of things. It's hard to say exactly. But based on the context that, hey, I've got here this next line thing that just read a string in, and I moved that into RDI, and I also just moved this thing, this quote, into RSI. It's called quote. These are the first two argument registers, RDI and RSI, and I'm about to call a function called strcomp that might compare two strings. It seems like a fair inference that RSI might be a pointer to a string. Okay, so on that presumption, let us check x/s. That's how you examine a memory location to see what's there. Here's RSI, And hey, that does look like a string. We need to talk about your flare. If you recognize that quote, pat yourself on the back. You are a true and proper nerd and understand the history of our culture. If not, go look it up and spend an hour when you're tired of debugging, by being entertained or so. At any rate, that's my target. Because this, like the sort of next line thing, the strcomp PB business isn't fibbing about what its intent in the world is. Instead, it's going to compare two strings just like standard strcomp does. And so if you recall, strcomp will return a number indicating the relationship between the two strings it compared. In the event that the two strings are equal, then it will return 0. However, if I do a next instruction right now, you'll see that the number that's returned here in RAX is definitely not a 0. And that accounts for the fact that these two are non-zero. Now, the next instruction is interesting. It tests EAX against itself. This is actually common for the compiler to do, and we'll talk about it in lecture as one of the efficient ways that folks can check for the zero equality, the truthy or falsiness of a return value or a variable out there, tested against itself. This performs a bitwise AND of EAX against EAX, but only sets the flags register that allows for conditional jumps to make their decisions. You can see on doing a test here, if I do a next instruction, well, I can't actually see the flags register here. If I make this thing down, you see over here, it has the 0 flag is not up here. And so the 0 flag is set and would dictate if it's set, then I would not jump on a JNE, but when it's down, it's false, then the JNE jump will be taken. Now that's no good for us because we'll take this jump and that will land us here at this failure. So before we sort of proceed on that, I want to mention as a hint that sometimes these failure messages that are going to be passed as a parameter to the failure function, they actually are potentially useful. Now you can see that if I step out of the debugger for a second here and just run this thing on the input.txt, the failure message is, this is not the quote you're looking for, move along, move along. That's accessible within the debugger as well. If I step one more instruction and then examine what's in RDI now, whoopsie, not percent, but this. Here's that quote. This is not the quote you're looking for. Move along. Let's see. So that's what gets passed in here. And so I encourage folks, look at those messages, and it is potentially useful then to get insight into what the sort of desired input might be. A lot of the clues are very esoteric, but if maybe they only make sense in retrospect. But hey, any hint is helpful in cases like this. So to that end, though, what we more or less derived what is needed in this case. It was an RSI and might still be. And so if I back up just a little bit in history and take a look at this thing, we need to talk about your flare. Let's zip over to our input.txt and plop down. We need to talk about your flare. Save that and come back over here. I'm just going to give this a shot on the command line to see how we did. And oh, look at that. Hey, we made it into phase 2. That's 5 points, so that's not too bad. In the debugger, I would maybe rerun at this stage and can sort of quickly step through a bunch of things here. So on this call to strcomp, assuming I've done my job right, and see here's RDI, that's my input. It is, we need to talk about your flare. On our SI, we need to talk about your flare. This strcomp should return a 0. If I do a next instruction, then yes, these two strings are equal. And so I won't take this jump and instead will fall through to return from this phase and get myself some sweet, sweet points. And you can even see those points getting added on here of like something gets moved around, and then that EAX, I think there's probably some access for the points here per points per phase, that gets added on then to some variable called score. And that's probably what my score is. So at that stage, I could futz around just a little bit, but basically I'm ready for phase 2, so only break at phase 2. And then I'll just continue at this stage, which will fast forward to the next breakpoint, and then can proceed with some analysis. It wouldn't be a bad idea here to put some more input in, so gibberish here. I'll just plop something down. I don't know if this thing is going to take a string or something else, but having some input there will help me to identify, oh, here's the stuff that's coming in here, so that's not too bad. And in terms of my breakpoints, I've got 2 of them, but I'm basically done with phase 1, so I'm going to disable 1. And that will then it's not enabled anymore, so it won't break there anymore. I'm going to rerun again so that the new format of my input, that gibberish here, that comes through. So I'm going to run again, but this time I'll break at phase 2 because phase 1 breakpoint is disabled. So we can start looking around here. It looks like there's subtraction from the stack pointer, so that's going to create some space in the stack. And then there's a bunch of weird instructions here that we'll actually talk about later in lecture as part of what GDB inserts for the canary values, and they're they're protected against buffer overflow attacks. They're the stack protector. So this sequence here is interesting, but not relevant to me solving anything. In fact, probably I want to move ahead here to this next line part, because we clearly saw earlier that the next line thing, that's where things come in. So I'm just going to move ahead a few instructions until we get here, and then just take a look at RAX. That's indeed the gibberish that I typed here. Okay, so in that respect, it's now probably time to look ahead a little bit here and poke around. I can see that there's some address for something that's getting loaded into RCX, and then the stack pointer is copied into RDX. Let's see, I can't remember what are RCX and RDX, what are those good for? Let me pull up that register summary diagram, see. Oh, that's suspicious. Okay, so RCX is argument 4 and RDX is argument 3. Are there changes to RSI and RDI immediately after that? Oh, indeed there are. Okay, so here's RSI. That gets changed. Oh, and I copied REX into RDI. So this is arguments 1, 2, 3, 4. This looks like it's setting up a function call. And indeed, scanf is getting called here. It's some puzzle bin version of that, but it's still scanf. Now, if you're not acquainted, it's not a bad idea to look those functions up. So I'm going to, in a terminal here, man scanf. This is the standard C library version of it. scanf family of functions scans formatted input according to the format as described. The format contains conversion. Hey, this is just like scanf. Except it reads from a string instead of reading from a standard input or from a file or something like that. Okay, cool. So that's handy to know about. There's maybe some more details in here, but I'm guessing there's going to be things like %Ds and Us and X's and S's for strings and so forth and characters. Okay, cool. Okay, so I'll want to be on the lookout then for a format string, because this scanf call, it's going to have some format string that's stored in global memory, and that'll go in. Actually, according to the calling convention for that, it has 2 required arguments. The string to read from here, and then the format string of what's going to be read out of that. And so that's good to know. This is arguments 1 and argument 2. Argument 1, we decided, is RDI. That's what came out of next line, so that was my gibberish here. And argument 2 is an RSI. I'm betting that's going to be a format string. So let's zip ahead just a little bit. And here, at that stage, RSI will then load it up with this global variable. If I examine that thing, expecting it to be a format string, ho, that definitely looks like a format string. There's a little %D. And that would mean 2 integers are supposed to come in here. And that would explain entirely why, the other 2 arguments, RCX and RDX, those were addresses. Those are locations where integers can be read. They're passed as the third and fourth argument to this. So it looks sort of something like this is like an scanf of inputs, and then here's a %d, and then this is like, see, num1 and num2, something like that. So this is the assembly equivalent of something that looks like that there. Okay, so that means gibberish here is no good, and my guess is that if I do a next instruction here to go over the scanf, this is going to return 0. It's going to compare this to 1 and jump if it's less than or equal to 1. It is. Most scanf functions return how many things they scan. In this case, neither of gibberish nor here are numbers, so we'll have read none. And so I'm gonna find myself in a failure here. If I just examined, hey, what is RDI in this case as a string? Better figure out which register has that format. So, okay, thanks a lot. That's, I just didn't, have the numbers in. So let's just plop down, like, here's 10 and 20 for this instead. I'll leave that there. I'll get rid of it later. Let's rerun. Okay. So here I'm at phase 2 again. I want to move ahead to the point of reading here from scanf. Now, hopefully this will be a 2. Yes, all right, it's 2, which means 2 are in there. Now, they should be at the following locations. The first one should be at the stack pointer. So let's see, I don't see a stack in here, but if I printed out the stack pointer, that's a memory location, but I want to say what integer, word size in decimal is there. That's where number 10 is at. And then if I looked 4 above that, at that, so let's say what's plus 4, hey, there's my 20. Okay, cool. And so both the inputs, they came in from the inputs.txt, they got put in the stack. And I'm betting after I, move ahead here, it's going to probably fish those things out. Yeah, indeed. Okay, so copying from the stack location, right at the top of the stack, that's where the 10 was at, and the 4 is plus 4 is a 20. That's copying it back into EX to do something with it. So if I did an X instruction, there's the 10 that plopped out. And I bet later on, yeah, here's some move 4 off the stack pointer in EDX. It's going to do something with that 20 that I had in there. Now, what it's going to do, that's up to all of you to figure out. But this should take you into the puzzle bin just a little ways, educate you a little bit about techniques you might use with the debugger. A few final thoughts about this. This is a pretty narrow window to be able to view the source code associated with Puzzle Bin in. And if you're clever and sort of paid attention in some of the lab work that you're doing, you'll know that there are some handy commands that you might use in order to say, take all of Puzzle Bin and disassemble it. Show me what code is associated with it. A handy one to know about is object dump. And it is used to disassemble various things. If you use the -D option, it will disassemble the text section, and doing so on Puzzle Bin will generate a whole lot of output over here. You can see that that's a bit much to display in a terminal, so I might just pipe it into some code.s or code.txt, and then in my text editor over here, I can look around and say, here's this code.s, close enough to assembly. Here's everything that was in Puzzle Bin. Like, you can't hide anything from it if it's there. So for instance, if I was looking around for phase 01, like here's all of that code associated with it. Not in a narrow debugger window, but instead available for me to like make commentary about, to take notes in case I'm interested in sort of following along with that. Super handy to know about, and I encourage everyone to make use of that kind of tactic because it will make your job a lot easier in terms of getting a global sense of what's happening. You can see phase 2 is much longer than phase 1 once we got through the initial phase, and then phase 3 is longer yet than that. All right. So that's probably enough by way of preamble for Project 3. It is challenging and probably the peak difficulty that we'll get in the semester. Have at it, gang. Have fun with it where you can. Struggle if you can, knowing that struggle is the path to learning. I will see you all in lecture soon, and happy hacking until then.